Hi everyone, my name is Clarissa. I'm from the Hong Kong University of Science and Technology. The title of my presentation today is Interconnect Structures for Reducing Intra-layer Metal-to-Metal Capacitances. First, let's start from the interconnect delay challenges due to technology scaling. Here is a cross-section image of an integrated circuit. It consists of the transistors and the interconnects. As technology scales into a smaller dimension, transistor speed increases and its delay decreases as shown in this figure. On the other hand, interconnect delay increases with smaller technology nodes. Therefore, as you can see, circuit delay is dominated by the interconnect. This is also reflected in the power consumption, as shown in this figure. Here you can see similar trend that most power is consumed by the interconnect. Technology scaling affects interconnect delay in increasing the resistance and the capacitance, therefore increasing RC delay. With scaling, metal-to-metal pitch is reduced, as well as the metal spacing and the metal width. The reduction in metal width results in resistance increase, while the reduction in metal spacing results in capacitance increase. To account for this issue, both R and C need to be reduced. There are a few methods. First is material engineering, that is by replacing materials used for a lower resistivity and a lower dielectric constant. However, reducing resistance is a challenge because copper is already having one of the lowest resistivity among all metals. On the other hand, the capacitance still leaves some room for improvement. As a reference, the commonly used material, silicon dioxide, has a dielectric constant or K of 4.2, while the minimum limit is K equals to 1. Another approach is by optimization of interconnect geometry, that is, the width, spacing, and thickness of the interconnect can be optimized to reduce resistance or capacitance. For example, metal thickness can be increased as a countermeasure for increasing resistance due to smaller pitch. Finally, another approach is in the system level optimizations, such as by routing optimization, but this is out of the scope of this work. Let's now first evaluate the first method, that is dielectric material engineering for lower capacitance. Low-K materials have been incorporated into the technology scaling scheme, as shown by the trend predicted by ITRS. It shows that the need for K reduction to below 2 in the future technology nodes. Material engineering technique used to achieve lower K is by introducing bonds to reduce dipole strength. As shown in this figure, there are various categories of materials, but K less than 2 is challenging to obtain using this method. To reduce K to below 2, porosity needs to be introduced to reduce the material density. This is illustrated in this figure, showing that dielectric constant decreases with higher porosity. However, mechanical reliability becomes a challenge. Mechanical strength is characterized by the modulus of elasticity, or the Young's modulus. The higher the porosity, the lower the Young modulus is. In order to prevent failure during the back-end of line process, the Young's modulus of dielectric materials need to be higher than 8 GPa, as indicated by the line here. Therefore, this also limits the K value that can be achieved. Mechanical strength degradation due to material porosity is exacerbated by the pore structure. Most common pore structures are spherical. They are randomly arranged, such that in high porosity, they overlap with each other intrinsically or due to the evaporation process. As a result, the interconnected pores create regions that are prone to failure. How this phenomenon further compromises mechanical strength is shown in this graph. We can see that the ideal model with periodic pores shows a linearly decreasing Young's modulus with porosity. However, with overlapping pores, Young's modulus degrades faster. This further limits the amount of porosity that can be introduced, which prevents a lower K value. Or in other words, this imposes a limitation in the material aspect. So other strategies are needed to reduce capacitance in interconnect. As mentioned earlier, capacitance can be reduced while taking into consideration the interconnect geometry. Here is a picture of metal lines and a possible configuration relative to other lines. There are capacitances in various locations of the metal lines. However, they can be simplified into two parts: the intralayer capacitance between two adjacent metal lines and the interlayer capacitance between two different metallization layers. As shown in this figure, smaller feature size is characterized by smaller metal-to-metal pitch. Under this scaling scheme, it results in contrasting trend for the two capacitances. The interlayer capacitance decreases with smaller technology nodes. It is because metal width also scales down. In contrast, the intralayer capacitance increases with smaller technology node, such that the total capacitance is dominated by the intralayer capacitance. How intralayer capacitance becomes more important with scaling is also due to the need for higher metal aspect ratio, which is defined as the thickness T over the width W. Because of scattering events in the nanometer dimension, with smaller pitch due to scaling, resistivity increases. As a consequence of the increasing resistivity, line resistance increases with scaling. So one possible solution is to increase the aspect ratio, which is by increasing the metal thickness T. And by doing so, line resistance can remain more or less constant with scaling, as shown in the graph. However, due to the thicker metal lines, the intralayer capacitance also increases. Therefore, this further shows the importance of the intralayer capacitance relative to the interlayer capacitance. As a summary, for reducing interconnect parasitic capacitance, the approach using porous low-K materials are limited by the mechanical strength or Young's modulus requirement. The problem is made worse by the random arrangement of pores. Thus, a method is needed to provide more order or alignment to the pores. On the other hand, we have also discussed the significance of intralayer capacitance relative to the interlayer capacitance. This means, to meet mechanical strength requirements, K in the interlayer can be relaxed, while capacitance reduction should be focused on the intralayer. So, an asymmetric dielectric with higher interlayer capacitance compared to the intralayer capacitance can be used. Here is one method to achieve a low intralayer capacitance compared to the interlayer capacitance. By arranging the porosity to be asymmetric in two directions, that is, in the in-plane direction and the out-plane direction, then the capacitance will also be different. We know that the pores have K value of 1, while the dielectric has a K value of 4.2 for silicon dioxide. Also, we know that capacitance in series is always lower than or equal to capacitance in parallel. So, by having parallel pores in the interlayer and series in the intralayer, we can achieve intralayer capacitance lower than the interlayer capacitance. To do so, the pores need to be vertically aligned. For example, by having pores in cylindrical shape. Thus, This simulates parallel pores in the interlayer and series pores in the intralayer. The resulting asymmetrical dielectric constant is shown by the simulation result as a function of porosity. We can see that the intralayer K in red is lower than the interlayer K in yellow. And the theoretical minimum is simply when the dielectric is divided into two parts, air and dielectric. As a reference, a common porous dielectric structure with spherical pores is shown in blue, with symmetrical dielectric constant in both directions, such that the K value is also in the middle between the intra and interlayer K. To obtain a vertically aligned porous dielectric, CNTs can be used as a placeholder, then it can later be removed. I'll describe the fabrication steps, and I'll also show the corresponding SEM cross-section. First, CNTs are synthesized from a nickel-aluminum-nickel multi-layer catalyst by PECVD. Zirconium oxide is used as an interface layer to enable CNT growth on silicon nitride edge-top layer. Then silicon dioxide is deposited to fill areas between the CNTs. Afterwards, the surface is polished to expose CNT tips. Then we use autoplasma to remove the CNTs. This leaves cylindrical pores on the dielectric. For a complete metallization step, the dielectric is etched for metal lines, followed by copper deposition. Finally, silicon nitride is deposited as an edge top layer. Here we show measurement results to demonstrate that the intralayer K is indeed lower than the interlayer K. First, both K is less than 2, with intralayer K 11.8% lower than the interlayer K. The measurement structures are shown here, which measure the interlayer capacitance on the left and intralayer capacitance on the right. The statistics or distribution of K is shown in this graph for both intra and interlayer K. The mean values are 1.75 and 1.97 for intra and interlayer K respectively. From these values, we can estimate the porosity to be 60%. Keeping in mind that we want to achieve low K with high mechanical strength, here is a comparison with existing technologies in terms of the trade-off between Young's modulus and dielectric constant. It can be seen that the proposed technology is among the lowest K for both intra and interlayer orientations. In terms of the Young's modulus, we can see a general trend that it decreases with lower K. However, the proposed porous dielectric has a Young's modulus of 15.7 GPa, which is larger than the requirement in the back-end-of-line process. This proves that the cylindrical pore structure improves mechanical strength by reducing randomness. That is, the structure provides alignment to the pores and prevents them from merging. To show how an asymmetric intra and interlayer dielectric can improve performance metrics of interconnect, we evaluate the RC delay of coupled metal lines. Here is an illustration of the simulated structure. A pulse is applied to one end of the middle line to measure the delay, while the surrounding lines in both intra and interlayers are grounded. Here shows the delay plotted against aspect ratio. As a reference, we use isotropic dielectric with the same average K value of 1.84. The proposed anisotropic dielectric shows smaller delay, and with increasing aspect ratio, the amount of delay reduction is more significant compared to the isotropic dielectric. This is shown in the blue line with the right axis. With our goal to effectively reduce the intralayer capacitance, Here is how far we've got. We have engineered a porous dielectric structure such that it has lower intralayer capacitance than the interlayer one. That is by using a cylindrical pore structure. The intralayer and interlayer K are 1.75 and 1.97. Then we have evaluated the application in delay reduction, and at the same time, the proposed porous dielectric structure is mechanically stable. What it means is that this approach can be used as a blanket ultralocate dielectric for both intra and interlayer levels, and it is intrinsically more effective in lowering the intralayer capacitance. However, can the intralayer capacitance be further reduced? Of course, there is a possibility of fine-tuning the pore density, size, or arrangement. But another possibility to reduce intralayer capacitance is to use two different materials in the intra and interlayers. Thus, the most straightforward material to use in the intralayer is air, which leads us to the air gap technology. As air has the lowest possible dielectric constant of 1, replacing the intralayer dielectric with air provides an effective method to reduce intralayer capacitance. To do so, an additional lithography step is needed to define the air gap regions between the metal lines, where air is used as the dielectric. In this case, the intralayer capacitance decreases, while the interlayer capacitance is not affected. For air gaps to minimize intralayer capacitance, its effectiveness depends on its size relative to the available space between the metal lines. That is, the air gaps need to fill the entire metal-to-metal space. Here, the air gap void size is smaller than the space. Therefore, it is not as effective as the one with void-to-space ratio of 100%. Also, ideally, this ratio should always be 100% regardless of the spacing for the intralayer capacitance to be minimum. One problem in the most commonly used air gap technology in the literature is that due to the deposition technique, there is sidewall dielectric, which thickness depends on the metal-to-metal spacing. Here is an illustration. In the lower metallization level with smaller spacing, there is very minimum sidewall dielectric. Therefore, the air gap size spans the metal-to-metal spacing. Compare this to the upper metallization level. The air gap size is smaller relative to the metal spacing due to the sidewall dielectric. This is not ideal. Similarly, this sequence shows increasing metal line spacing and how air gap size decreases with larger spacing, until it eventually disappears at larger dimension at a few microns. To solve this issue, which is to obtain 100% void-to-space ratio, we need to prevent material deposition into the air gap regions. One method is to use 2D materials and the transfer process. The 2D materials is transferred as air gap capping layer. Here is a fabrication steps. First, we synthesize hexagonal boron nitride or HBN on a copper foil and then coating it with PMMA. Then the copper is dissolved in FeCl3 solution and then it's transferred to DI water. For the interconnect layer as the substrate, let's start from a metallization layer. Air gap region is patterned between the metal lines. Then the HBN layer is transferred to the substrate such that the HBN and PMMA are both suspended on the air gap region. PMMA is then etched by annealing, and finally etched top layer and the subsequent interlayer dielectric are deposited. Here are SEM pictures at various stages of the fabrication process. After the transfer process, this is a top view and this is the cross section. And here is a top view showing an interdigital capacitor to show the density of the defects, which are holes on the suspended HBN. As you can see, the defect area is 1.1% of the total air gap area. Here are SEM cross-sections after the passivation by interlayer dielectric. We can see that the air gap void size is 100% at both smaller or larger spacing. While we have shown that laterally we have achieved air gap width to span metal-to-metal spacing, in the vertical dimension, the suspended HBN layer do not lay entirely flat on the interconnect trenches. Instead, there is some sagging. So we perform characterizations by AFM on the suspended HBN. First, we characterize the number of HBN layers, and based on the average thickness, there are around 30 layers. For the suspended HBN, here is a 3D image, and here is the profile extracted. As we can see, the amount of sagging depends on the air gap size. However, this is relatively small as it is only in a few tenths of nanometer compared to the total metal thickness in 1 or 2 micrometer. Therefore, the reduction in air gap volume as well as the increase in intra-layer capacitance is insignificant. So now we compare the effectiveness of various air gap technologies in reducing intra-layer capacitance based on the void to space ratio and the effective K value. In terms of the void to spacing percentage, this work demonstrates the highest void to spacing value and less dependence on spacing, as we have demonstrated almost 100% void at available spacing of larger than 2 micrometer. As mentioned earlier, the effectiveness of air gap depends on the void to spacing percentage. So, as shown in this figure, this work reduces intra-layer capacitance the most compared to other technology. To evaluate how air gaps can be used to reduce intra-layer capacitance, we show capacitance reduction as a function of aspect ratio, which is defined as T over S, as before. Using the average K as a reference, the intra-layer K is significantly lower than the interlayer K. As a result, intra-layer capacitance is reduced significantly. This can be seen from the capacitance versus aspect ratio plot. The symbols are measurement results and the lines are projections. The isotropic intralayer K equals to interlayer K is shown by the dotted line. This is by assuming K equals to 2.6, which is the average. We can use either silicon dioxide or the average K as a reference, and the percentage of reduction is shown in this figure by the blue and yellow solid lines respectively. Then we can see that the capacitance reduction is more significant than the cylindrical porous dielectric structure. Also, this trend can be seen from the intralayer effective K. As a conclusion, we have identified the increasing importance of intralayer capacitance compared to the interlayer capacitance in advanced technology nodes. Therefore, capacitance reduction should focus on the intralayer dielectric. And to do so, we have proposed the use of asymmetric porosity in form of cylindrical porous dielectric, such that the intralayer dielectric constant is lower than the interlayer. We have also demonstrated that cylindrical porosity exhibits superior trade-off between mechanical and electrical properties. This approach, using the same porous electric material for both intra and interlayer. On the other hand, intra-layer capacitance can be further reduced using two different materials for intra and interlayer separately. In this case, we have improved the efficiency of air gaps in reducing intra-layer capacitance by having void-to-spacing ratio close to 100%. We have also discussed the fabrication technique using HBN as an air gap capping layer. Then, we evaluate the performance in intra-layer capacitance reduction with respect to the aspect ratio. So that concludes my presentation. Thank you very much.